Okay, so we are doing number 3, which is asking us to find the general solution to this Cauchy-Euler differential equation, x squared y double prime minus 3x y prime plus 4y equals x squared over the natural log of x. So let's find the solution to the homogeneous case. So x squared y double prime minus 3x y prime plus 4y equals 0. And we know that y equals x to the r is a form of solution to this. And finding y prime and y double prime, we can plug these into our equation and then solve for r, which I did here, here, and here. Now notice that when we multiply this x squared into the parentheses, the 2 will cancel with this minus 2, leaving us with x to the r. This x to the 1, or the 1 will cancel out with the minus 1, leaving us with x to the r, and then we just have x to the r right here. So now we can factor out an x to the r, leaving us with r squared minus r minus 3r plus 4 inside the parentheses. And if you've done a million of these, you probably would have just skipped straight to this step. But anyways, combined like terms, we have r squared minus 4r plus 4, which factors into r minus 2 squared, and that gives us r equals 2 with a multiplicity of 2. Or r equals 2 and 2. And that was one of the cases for our r value, which means that y1 equals x squared and y2 equals x squared times natural log of x. And our complementary solution is just c1 x squared plus c2 x squared natural log of x. Now we can find the particular solution. So we have this equation of our particular solution equals u1 y1 plus u2 y2, such that u1 prime y1 plus u2 prime y2 equals 0, and u1 prime y1 prime plus u2 prime y1 prime equals our function from the right side of the equation divided by x squared, because you can do that. And now I just plugged in our y1 and y2 in, and I wrote our equations here as a system of equations so that we can solve for u1 prime and u2 prime, and ultimately for u1 and u2. Now this is just the derivative of x squared, and this is the derivative of x squared times natural log of x. And now from this top equation, I got that u1 prime equals negative u2 prime times natural log of x, because I just subtracted this over to this side and then divided by an x squared. And now that we have this, we can plug it in for our bottom equation right here for u1 prime, which I did here. Now we can multiply this 2x into the parentheses and multiply this u2 prime into the parentheses. And notice now we have two terms that can cancel, leaving us with just these. Divide an x onto each side. We have u2 prime equals 1 over x times the natural log of x. Plug that in for what we had for u1 prime right here. And the natural log of x cancels with this natural log of x on the bottom, leaving us with just negative 1 over x. Now we can integrate these and solve for u1 and u2. So for u1, I took out a negative. So we have negative integral of 1 over x dx, which everybody knows is negative natural log of absolute value of x. And I forget if we're allowed to remove the absolute value signs, so I will just leave them in just in case. Now for u2, we have it equal to the integral of 1 over x times the natural log of x dx. And we can substitute natural log of x for smiley face. Take the derivative, we have d smiley face equals 1 over x dx, which we have right here. Which means we can now write this integral as the integral of 1 over smiley face d smiley face, which gives us the natural log of the absolute value of smiley face. Plug natural log of x back in, we have the natural log of the absolute value of the natural log of x. Now we can plug these into our particular solution, which I did here, and I just moved that negative out. And we have this right here. Pretty awesome. Now we just add that to our complementary solution, which is right here. And our general solution to this Cauchy-Euler differential equation is c1 x squared plus c2 x squared natural log of x minus x squared natural log of absolute value of x plus x squared natural log of x times natural log of the absolute value of natural log of x. Awesome. And that is it. Thank you for watching.